Setting up a reaction table. Okay, so the whole idea of an ice table or a rice table, if you prefer, is to use algebra to relate the changes from the initial concentrations of reactions and products to the concentrations of the reactants and products at equilibrium. So usually it's a case of fill in what you know and work out what you don't know. So in this particular problem, we've been given the initial moles of the methane, which is the 0.3, and we've been given the initial moles of the hydrogen sulfide, which is 0.4, and we've been given the initial moles of the copper disulfide, which is 1.1. And we haven't been told that we have any hydrogen, so we can safely assume that there is 0 moles of hydrogen initially present. To work out the change row, you're always going to look at your balanced chemical equation and just substitute in X in terms of the change in number of moles or concentration or whatever of one of the reactants or products. So it's usually best to let X equal one of the reactants or products that the stoichiometric coefficient is 1 in order to make the math a little bit easier. Now, in this case, I'm probably going to make a little bit of an assumption that the reaction is going to proceed primarily from the reactant side of the product side in order to get to equilibrium, based on the fact that I have 0 as my concentration of hydrogen. However, what you should really do to be thorough is actually work out your reaction quotient, which is using your equilibrium constant expression and substituting in the non-equilibrium or the initial values. So I'm going to go ahead and write an equilibrium constant expression for this particular equilibrium, just to be thorough. So H2 to the power of 4. Let's make this a bit prettier so we can all see what we're doing. And then on the bottom, oh, I've got them on my Mac, it doesn't let me do that, right. And then on the bottom, we will have CH4, the methane, multiplied by H2S to the power of 2. So again, I'm just going to tidy this up and make it look a little bit prettier. So if I substitute in those initial values, which are non-equilibrium values, the number I get out of substituting to my equilibrium constant expression will not be K, it will be Q, the reaction quotient. I'm going to give it a Q. So that will be initial concentration of CS is 1.1 times H2 will be 0, which will be to the power of 4, divided by 0.3 times 0.4, which will be to the power of 2. Okay, so if I bung that all in my calculator, I'm going to get Q equals 0. I can see that from my 0 to the power of 4, so that is going to be less than K. Okay, so Q equals 0, which is going to be less than my equilibrium constant K, which I haven't actually been given this time. So I can't actually go ahead and work out those equilibrium concentrations in terms of actual numbers. We're just going to do the algebra today. So that's going to tell me that the reaction will proceed to the right. So you do have to be a little bit careful with that if you have real world problems. You don't have something nice and easy that the initial concentration of one of your products is 0, because you do need to know which direction the reaction is going to proceed in. So we're going to allow the change in number of moles of carbon disulfide to equal X, because that's what ALEKS has given us as a breadcrumb. But if you were doing one of these problems and you didn't have that breadcrumb, it would be smart to either choose the methane or the carbon disulfide. And remember, because our reaction is going to the right, my reactants are getting used up and my products are forming. So we are going to reflect that in my change row in terms of X by if something is getting used up, it's going to get a minus in front of it. And if something is being formed, it will get a plus in front of it. So the change in then the number of moles of carbon disulfide will be plus X because its stoichiometric coefficient is 1 in the balanced chemical equation. If we look at the equation, for every 1 mole of carbon disulfide, we're making 4 moles of hydrogen. So that relationship in, for every 1 mole of carbon disulfide, we make 4 moles of hydrogen. We must reflect in the change row. So this will be plus 4x for the change in the concentration number of moles of hydrogen. All right, so what about my reactants? Well, my reactants are 1 mole of methane. So for every 1 mole of carbon disulfide that is being formed, minus 1 will be the change in methane. So for every X moles of carbon disulfide that is forming, X moles of methane are being used up. So I'm going to put a minus in front of the X. Similarly, for the hydrogen for the hydrogen sulfide, there's 2 moles of hydrogen sulfide in the balanced chemical equation. So for every 1 mole of methane that gets used up, 2 moles of hydrogen sulfide get used up. So that is going to be minus 2x. Okay, so to work out my equilibrium row in terms of x, the general idea is to get the equilibrium concentrations, or number of moles or whatever. It is going to be the sum of the initial row plus the change. So you're just going to go down the column, okay? So I quite often write it like this in class to remind people initial plus change will equal equilibrium. So you're just going to do that sum down each column to get your equilibrium values. So for the methane column, we'll end up with our equilibrium concentration expressed in terms of x of 0.30 minus x, okay? And then for my hydrogen sulfide, 0.4 minus 2x will be my equilibrium concentration in terms of x. I have to make this a little bit smaller to fit in. In my carbon disulfide column, initial plus change will be 1.1 plus x. So there's my equilibrium concentration in terms of x. And for my hydrogen row, initial plus change would just be plus 4x. So 4x. Okay, so if we actually had the equilibrium constant, we could then take these equilibrium concentrations in terms of x and substitute them into our equilibrium constant expression. And that would allow us to rearrange and solve for x, which you have to remember what substitution you made for x. So in this case, we substituted the x for the change in number of moles of carbon disulfide. And then if you were asked for equilibrium concentrations, you could then substitute x into whatever equilibrium concentration you were trying to calculate.